like to request the narrator of the video, which is the youngest member of our team, Miss Rita Mehman. She's a third-year medicine student here in the UK, to please introduce our guest speaker. Rita, over to you.
Okay, hello everyone. It's an honor to introduce Professor Amos Winter today. He has a very extremely impressive profile. So Amos Winter is an associate professor of mechanical engineering at MIT. His research focuses on machine and product design for developing and emerging markets. Professor Winter earned a BS from Tufts University in 2003. He did his MS and PhD from MIT, all in mechanical engineering. He received the 2010 Tufts University Young Alumni Distinguished Achievement Award, the 2012 ASME Award, and the Pi Tau Sigma Gold Medal. Amos was named one of the MIT Technology Review's 35 Innovators Under 35 for 2013. He received the MIT Edgerton Faculty Achievement Award and an NSF Career Award in 2017. Professor Winter is also the principal inventor of the Leveraged Freedom Chair wheelchair, which was a winner of the 2010 R&D 100 Award and was the subject of Engineering Reverse Innovations winner of the 2015 McKinsey Award for the Best Article of the Year in Harvard Business Review. Without further ado, I'd like to invite Professor Winter to take the stage for today's talk. Thank you.
Thank you for that introduction, Rita, and thank you everybody for tuning in today and listening to me speak. Let's see, I need to have approval, I guess, from whoever's coordinating the Zoom call to share my screen. Okay, now I have it, great. There we go. And I assume everybody can see that okay?
Yeah.
Yes, Professor.
Great. Thank you, Rita. Okay, great. So today I want to talk to you about some of the work in my research group, and I think it dovetails quite well with what you're trying to achieve with the establishment of your university, in that we're promoting engineering, we're promoting rigor in science and technical work, while also having an eye on sustainability. And that is certainly a core theme in a lot of the work that my group does. And my talk today is going to be about some of the techniques that we use around trying to bring together hand in hand technical insights that you get from conventional technical focused research, as well as socioeconomic insights that are very unique to the markets, particularly developing countries and emerging markets. And bringing those together in order to see opportunities for new innovations and new products that can impact people's lives, and in some of the projects I'm going to talk about, improve sustainability, not only in developing countries, but really global markets. And in a real common theme in what you're going to hear about today is trying to achieve some high performance technology, but that's also low cost, that can work in resource constrained settings, but also provides a very high value solution back to wealthy markets. And an example of this you'll hear a bit more about later is the desalination system shown in this picture. And also why I chose this picture is because I think it really represents what my group is trying to do in our projects, is that we're not just a research group that is working only in our lab at MIT, only looking at our computer screens here. We are really operating throughout the world and collaborating with partners all over the world in the communities that we are trying to impact. And so this picture was taken in India about 1.5 years ago with our partners at Tata Projects, which is an infrastructure company that does water systems throughout India, and is part of the Tata Group, which is a big multinational. So there's members of the Tata team, members of our team, and it was great to come together to make this happen. So, and finally, as you heard in the intro, I'm a professor of mechanical engineering, and the name of my research is the Global Engineering and Research Lab. So again, we're really trying to denote that global perspective in the work that we do. So to start out, I want to just reflect for a second on why production to execute compared to the product design that's been historically done, that's been focused on wealthier countries. So if we take indicators of human health and well-being, many of which can be satisfied with products like, like water purification systems, like sanitation systems, like healthcare systems. We can look at indicators like the United Nations Sustainable Development Goals, and these all give actual measurable quantities or changes that we need to make as a society in order to raise the quality of life for people around the world. And this is important because there's about 1 billion people still in abject poverty, about 2 billion without clean access to clean water, about another 2 billion without a toilet. So really, really big problems. But what I think is interesting as a product designer and an engineer, when you look at these metrics, what's interesting is that we have solutions to a lot of these problems. If you're fortunate enough to live in the United States or Europe, I think most people there do not worry about clean water, do not worry about sanitation. We have, low infant mortality rates because we have good health care. So it's not an issue of no solutions, it's an issue of solutions have not been brought or mapped over to poor communities for some reason. And I think that reason stems from a price-performance mismatch. So if you take any family of technologies, let's take the automotive sector, for example. That family of technologies will lie on a nonlinear curve where up at the top, say in the car example, you'll have like a Ferrari, which costs a lot of money and gives you relatively high performance. And then if you want to compromise performance a bit, you can spend a lot less money and buy maybe a Toyota Camry. But you can move along this technology curve and you'll have this nonlinear scaling between price and performance. And the issue I think that exists in poorer countries is that consumers still demand a good level of performance for particularly these technologies that impact human health and well-being. Nobody wants a semi-functional toilet or semi-clean water. The problem is the price point that can be afforded by those countries may be lower than what we pay equivalently in wealthier countries. And this creates a mismatch in that there's no way you can adapt your way down this existing technology curve to meet that unique price and performance point of poor countries. You have to somehow find a whole new solution space. So this is what my research group does in 3 stages to try to engage these new solution spaces and create new solutions that can work in poor and rich countries. So the first is we try to elucidate new markets by characterizing what is unique about them from a socioeconomic and technical perspective so we can understand constraints and requirements and really hone or zero in on what this new price performance point is. Then what we do is we leverage what an organization like MIT is best at, is engineering science, rigorous engineering, product design, fundamental technical insights, in order to create these new disruptive solutions to make this leap from the existing technology curve to this new price performance point. And then finally, we don't just focus on this point in say, a poor market. We try to imagine, boy, what if we could grow an entire new product line out of that point and do this process called reverse innovation, where we go back to wealthy markets and provide a lower cost, but as good or even higher performance solution, and then create a product family for rich and poor markets alike. So my research group tries to go through these 3 stages. And I guess my background in this area comes from actually living this experience personally. And so in the intro, this wheelchair was mentioned, the leveraged freedom chair, which we initially designed for rough terrains in developing countries. These shots were taken in India. And then what we did is took the same core DNA of that product, changed some of the features and in the fit and finish a bit, and created a version for the US European market. And so this has become a profitable company that does about 400 units per year. And so we experienced this reverse innovation process where we could leverage the same technology and have it be very effective in poor and rich countries alike. So today I'm going to give you 3 examples from my research group that I think really demonstrate these three phases of how we do innovation in product design for developing and emerging markets. I'm going to talk to you about water purification using solar-powered electrodialysis desalination. I'm going to tell you a bit about our high-performance, low-cost prosthetic feet. And then I'm going to wrap up by telling you about low-pressure and solar-powered drip irrigation systems that we've created. So to start out with the desalination work, about 9 years ago now, 8 or 9 years ago, my group started working in India, and we started interacting with a big irrigation company, Jain Irrigation, who said to us, you know what, we work with water, we work with poor communities. A lot of these poor communities don't have access to clean drinking water. We should be able to do something about it, but what do we do? And I'm highlighting this point in a process at the beginning because it's so critical, and I think a point of error for a lot of groups, particularly in academia, because it's so easy to just jump to a solution. We could have so easily said, we're going to make a water filter, we're going to make a reverse osmosis system. But what turned out to be so critical in this project was taking a big step back and asking ourselves, well, what is the problem? What makes water dirty? Who does it affect? And what is the solution space that could be used to address it? So as we dug into the Indian water market, what we found is actually the most prevalent contaminant in water for the country is salt. And this map is showing every color other than blue throughout the country is salty groundwater that's actually too salty to safely drink per World Health Organization standards. And it impacts about 60% of the land area of India. And most of the country, about 70% of the country, gets their drinking water from groundwater. And so as we looked into this and understood the communities that are affected by this, we realized too that by far the most impacted segment of the population is rural communities of 2,000 to 5,000 people, rural villages. And about 60 to 70% of those villages still don't have reliable power supplied by the electrical grid. But we realized an insight that when we looked at the solar irradiance throughout the country, how much sun power is available, it actually matched up quite well. This is a map of solar radiance. It matched up quite well in that where you have the most solar radiance is also where you have the saltiest water. But we ran into another barrier in that we started working with a big infrastructure company that makes water purification systems. They've done over 3,000 village scale systems throughout India. And what they told us was that, boy, when you try to go off the grid and go to these rural communities and try to use solar power to run existing desalination systems, it more than doubles the capital cost and it makes them too expensive. So we haven't been able to tackle that market. So what we had to do at this point was understand what technologies could we maybe use that could be more amenable to this off-grid market and be cost-effective. And we surveyed many, many different technologies. We did the analysis on them, you know, the energetics, thermodynamics. And what we realized was that reverse osmosis, which is the industry standard, most of you have probably heard of this, was one candidate. And then the other one that stood out was electrodialysis, which is a well-established technology, been around for over 50 years. And what made it stand out was that for the salinity ranges that we typically find in India, electrodialysis required only about half the specific energy to remove salt from water versus reverse osmosis. And why that was important is that if we wanted to go off the electrical grid and do a solar powered system, we could use a solar power system about half the size as we would need for reverse osmosis. Furthermore, we realized that these small-scale reverse osmosis systems that are used now waste about 60% of the water that come into them, but electrodialysis for these salinity ranges can cut that waste down to only about 5 to 10%. So we established this pretty compelling opportunity for disruption in this market, and because we did this detective work in background research, we were able to build quite a large team now over the last few years and quite a lot of funding sources in order to realize this solution. And the reason I walked you through this detective case is I really want to impress on you how important it is to do that background work to understand those socioeconomic and technical constraints that are unique to the market, because they will give you insights into innovative and viable solution spaces. So what we've done now over the last few years is started creating these new technologies. And this is a picture of our very first village scale system that we made for a USAID program. The USAID is our country's agency for international development. We ended up winning this program. And then we've done a series of other field pilots throughout the world. And this is another important part of what my group does, is that we don't just do theory on paper. We build real hardware and build full-scale systems to understand what are the real life ramifications of the technology that we have to consider and design for. And the big insights that have come out of this work is how much we have to reduce the cost of this technology. So the first solar-powered PV-ED system that we made was $63,000. Most of that was in this unit, the stack, which was about $40,000. This is the unit that takes the salt out of water. And in comparison, current RO systems of this size are about $5,700. So we had to somehow cut the cost by about 10 times to be viable in this market. So over the last 10 years, or sorry, last 7 years, 8 years, we've come up with a variety of innovations to do that. And this slide really summarizes the crux of how we've been able to cut costs so substantially. So this is a picture, this is a picture of one of our newer PV-ED systems. And what is unique about this is it actually can change its power consumption throughout the day in order to match the rise and fall of the sun. And so at every point in time, it's looking at the sun and constantly adjusting how fast it moves water throughout the system, so how much pumping power it uses, and then how fast it's extracting the salt out of the system, by how much power it applies to this electrodialysis stack. And by doing that, we can raise the power throughout the day, shown in these purple bars, where each kind of tooth of this sawtooth pattern is a batch that we run throughout the day, and we can accommodate that solar change. Now, in comparison, how you typically run a solar-powered ED system is with fixed power level batches throughout the day. That's this blue sawtooth pattern. And by doing that, what you have to do is collect energy in batteries in the middle of the day and then use it at the end of the day. But with our technology, we don't have to do that. And we need minimal to no batteries to still produce the same amount of water in about half the amount of time. So with these innovations, what we've been able to do is, first we started with reverse osmosis as our benchmark. And this is showing cost as how much cost it is per volume of water you can make. Then this was our first ED systems that we made that ran with these blue sawtooth curves. And now our newest technology has come down to a price point that we think is going to be about at par with on-grid RO. And what's really exciting about this is these PV-ED systems, the cost includes the cost of the solar panels, that whole solar system, whereas on-grid RO, you don't have any capital cost in your power system, you're just buying the recurring cost of the energy. And so even with that bigger capital cost, we make it up with the recurring costs, and we can make cheaper off-grid. And what we see is quite viable and quite compelling from a business perspective, PV-ED systems. Okay, so that last project represented how we need to look into markets and understand their constraints and requirements to see innovation opportunities. This project, I think, really highlights how we can use engineering science to create new disruptive innovations. And so this project's focused on high-performance, low-cost prosthetic feet. And the backstory is that we started linking up with an organization, again in India, about 9 years ago, that makes the most widely distributed prosthetic foot in the world, called the Jaipur foot. And there's actually a number of these that are distributed in Pakistan as well. And this has been successful as a product over the last about 50 years because it looks pretty lifelike. It's flexible if you need to squat down and use a toilet. And because it looks lifelike, it also enables people to not be to not stand out as much if they're walking barefoot, say, when they're praying in a mosque. And this is important because there's still a lot of stigma against people with disabilities. And so Jaipur Foot came to us a number of years ago and said, boy, we'd like to make an improved product because our current foot is too heavy and it's handmade and it's actually not compliant with international standards. And then in addition to this picture here, just to give you a sense of this, that from a user perspective, people also want to be able to walk normally. They want to be able to walk with as close to able-bodied kinematics as possible. And this goes back to the stigmas against disability, that if a person looks like they're disabled, they may be less likely to have a job or fully participate in their community. So they wanted feet that could perform very well. And so this created a motivation for creating a foot technology that was high performance, low cost for developing countries, mass manufacturable. And so we had to figure out how to create that. And that motivated the critical research question here, is that how could we quantitatively and predictively think about the mechanical design of a foot and the biomechanical response it would induce. And what was interesting as we dug into this question is the entire prosthetics community hadn't ever answered this. There was no theory to connect the mechanical design of a foot to its biomechanical performance. And so the way we tackled this was to break it down to fundamental physics. And the way we thought about a foot was just like you'd think about a spring, because a foot, in a sense, a prosthetic foot is a spring. It stores energy and then it releases it to help you walk. So with a spring, if you apply a force to just a linear elastic spring, you'll deflect the spring, and so you'll get some deflection due to that force. And you can relate that force and deflection through a constitutive relationship, which we represent with K, the spring stiffness. Now we can do the same thing with a prosthetic foot. And what was unique about our approach here is we looked at the foot as a black box. We didn't think about a specific architecture from the beginning. Instead, we thought about, okay, we have the person's leg, and we want that leg to move through space and time. And what's powerful about thinking about the person's lower leg is that is the part of their body that they still feel and perceive, and that's their connection to the prosthetic limb. So we can look at the prosthetic foot as a black box, so long as it can induce the right motion and over right time of the lower leg, so produce the right kinematics. And so what we did is said, okay, we want a certain kinematic response when we apply a certain loading response. So of ground reaction forces, GRFs, applied at the center of pressure as you go from heel strike to the toe off, we wanted the correct response of movement relative to those forces. And what we could do then is optimize the foot to do that. So we'd optimize the stiffness and geometry of the foot to induce that correct constitutive relationship that gives us the right pairing between input forces and output motions. So we built up a fully theoretical model of how that works and used it to design new foot architectures that could replicate very close to able-bodied biomechanics. And this is an animation of that model operating of one of our feet stepping through a step over time. And so what that looks like when a person wears it is here's a step slowed down, and then here's the foot in relation to the person's body. And so now they're heel striking. But again, right now, I want to point out another important part of this project is that you'll notice this foot looks nothing like an actual foot. And as I said before, the aesthetics are very important to people. So we couldn't just be myopic engineers and just think of the energy transfer in our prosthetic foot. We had to also think about the cosmetic covering and how we make it look lifelike. So we had to also develop what the cosmetic covering looks like so it can look like a person's normal foot. So as far as the scientific results that have come out of this project, what we've been able to create is this framework to design prosthetic feet that can actually be customized to individuals. And so you can think this has a lot of relevance to maybe 3D printing feet in the future. Let's say in either wealthy countries or maybe remote clinics. And we can do it out of plastic. All these feet are made out of plastic. And what we're showing in these pictures is that these users that we made feet for vary quite a bit in their body mass, and that changes the design of the foot quite substantially. But when you look at their performance of how they walk in the plots below, this is showing the forces on the foot, the movement of the center of pressure from heel to toe going through the step, and then the kinematics of that lower leg segment, the X, Y, and angle position of that shank, the lower leg segment. Our feet perform very, very close to the able body data in these dashed lines that we optimize them for, even though our users span quite a range of body weights. And then we've also compared our feet to clinically prescribed leading carbon fiber feet, which cost thousands of dollars, as well as a benchmark carbon fiber foot that's an industry standard. And our feet perform just as well, even though they cost tens of dollars, made out of plastic. So again, this is going back to the point I made about making this high performance, low cost foot or any product. And we've been able to do that. Our foot costs dramatically less, but doesn't compromise performance. And so we've been able to see that they're accurately able to induce able body motion, and our feet cost about $5 worth of plastic as far as material costs, and are performing about as well as feet on the market that cost over $1,000. So going back to that need to make a lifelike looking foot, we've also teamed up with Vibram. Many of you may recognize this logo because it's probably on the bottom of your shoe, or at least on the bottom of your hiking boot. This is the world leader in hiking boot sole design and manufacturing. So we've teamed up with them to design a sole that balances looking like a lifelike foot, but also offering features that help preventing slipping, like in wet and muddy environments, and that can encapsulate our internal structure that absorbs energy and releases it to make a person walk very well. So last year we completed a 15 subject field trial of these feet, and they've worked incredibly well. There's no degradation of the foot over 8 months. People were more agile and could complete a mobility course faster. They could walk faster by about 10%. And in qualitative scoring feedback, they scored our feet higher than the existing Jaipur foot. So this has been all very, very compelling, and we are now making a big push to commercialize this because we're quite confident this will be a transformative product throughout the world. So the last project I want to talk about that I think really highlights global opportunities for technology is on irrigation. And so this picture that you're looking at is of a conventional irrigation system called furrow irrigation or flood irrigation. And the reason irrigation is such a compelling problem is that throughout the primarily developing world, there's about 2.5 billion small farmers who live on about 500 million small farms. And the most high impact development intervention you can do for them is help them irrigate, because then they can grow more and higher value crops on their land, make more money, and get out of poverty. But the problem is, you can't just convert all of these farmers to using flood irrigation like I'm showing in this picture. And the reason is, particularly in water-stressed countries, like certainly parts of Pakistan and India and parts of the Middle East, water's already in short supply. And so in India, for example, the replenishment rate of water is projected to be less than the water usage rate within the next 10 years, and within the next 5 years. And already 70% of water used globally is for agriculture. And so what we're using in this technology, in this project, is an irrigation technology called drip irrigation. And this is a means of placing drip emitters at the crops where you just drip out the exact amount of water the crop needs. And so you minimize water wasted to evaporation or drainage in the soil. And so drip irrigation can, one, provide farmers big benefits of more crop growth and growing about 50% more crops than they could with rainfall. And it also reduces water consumption versus flood irrigation, like in this picture, by upwards of about 60%. Now, as far as a global market opportunity, this graphic is showing the relative size of total cropland throughout the world, shown in the green circle, how much of that cropland is irrigated, shown in the blue circle, and the small little red dot in the middle, which represents how much of that cropland is irrigated with drip irrigation. So there's huge opportunity to grow the market segment of drip irrigation. So there's a great business opportunity as well as a great humanitarian impact opportunity by promoting drip irrigation. Now, this is a simplified schematic of a drip system. And this is a system that's pulling water from a surface source like a pond or a river or a canal. And so that water comes through a pump, which distributes it to the field, and the water comes out from drip emitters onto the crops. Now, the issue right now with conventional drip irrigation systems is they typically need about 1 bar or 1 atmosphere of pressure to induce the proper flow rate for the crops. Why this is an issue for the markets we're looking at, which are primarily off-grid, is that it creates about a $3,000 per acre system cost, whether you're operating with solar power or diesel, which is exorbitantly expensive for small-scale farmers. And so what we've tried to tackle in the technology of this project is reducing the main cost driver of this price, which is the pumping power required to move water through the system at this pressure. So what we're working on is designing drip emitters that operate at about 1/10 the pressure. By doing that and changing nothing else in the system, you can cut the system cost by about in half. And depending on where you are in the world with different subsidies, you can bring the cost very far down so it's affordable for a farmer within a year and a half payback period. And this is not only a technology that can impact poor farmers throughout the developing world, this technology is just as relevant for large-scale farmers who want to save energy costs and use more water-conserving technologies on very, very large farms, say in California, in the United States. So what we had to do here was figure out how these drippers work and how to make them run at lower pressure. So the drippers that we design are called pressure compensating, which means they manipulate their flow resistance to maintain a constant flow rate even when you change pressures. And what we want is drippers that at around 0.1 bar deliver the flow rate that we want for different crops. And the challenge is that existing products, as I said before, only hit that operating pressure at about 1 bar. Now, what we did is we opened up the drippers and understood, these governing features and these little geometric features that govern the flow geometry. And what was interesting as we started digging into this in reverse engineering how these products worked, we realized that one, this technology was first patented in the mid-1940s as a flow restriction device and was popularized starting in Israel in the 1970s. But since then, nobody had ever mathematically characterized why these drippers behave the way they do and how inside them this little flexible silicone membrane interacts with all these flow features to generate that pressure compensating behavior of a constant flow rate with variations in pressure. So the main features that do this are the orifice where the water inlets, the lands where the water flows over, and then there's a little channel that's cut into the lands where when the membrane deflects down and contacts the lands, all the flow is directed through that channel. So what we had to do was mathematically characterize the dripper, and this is showing 2 orthogonal views cut through the dripper. So here's the membrane and the orifice. And so again, the membrane, the orifice, the lands, and the channel. And then what we did was build up a full analytical model of how the dripper behaves. So how pressure on the inlet and flow rate through the dripper affect deflection of the dripper membrane and cut off the flow of the channel. And so my point of showing this slide is that we figured out this problem by understanding the physics governing how these drippers behave. So we had to understand the market and understand the technology. So what came out of that is we were able to fully analytically characterize the behavior of these drip emitters, put that analytical model into an optimization routine, and optimize all the little flow features inside the dripper to operate the dripper at a lower pressure. And so this plot is showing data of our new dripper design, shown in red, which has an activation pressure of 0.15 bar, and 3 other commercial drippers, which operate at about 1 bar. And so the ramifications of this work are pretty exciting, that for a drip system, any drip system, on-grid, off-grid, doesn't matter, you can literally just plug in our drip emitters, turn down your pressure, and operate at about half the pumping energy and pumping power as existing systems. And then that particularly has a lot of ramifications for off-grid systems in that we can reduce the system cost by about 40% versus current off-grid drip irrigation system technology. So again, we don't just work in a lab, we actually try our stuff in the real world. And We've now been operating a field pilot for 2 years in 9 locations in Jordan and Morocco, sponsored by USAID, where we have been testing in real field condition environments our emitters, which operate at 0.15 bar, half the pumping power of other commercial products, versus common commercial products in these markets that operate between 0.5 and 1 bars. And that we've shown that our drippers produce pumping energy by 43% through those trials, and actually demonstrated that we are achieving the energy reduction that we anticipated. And it's been quite exciting to see farmers come to us and say, oh my God, this is awesome. I immediately understand the value. How can I buy these? And so we are, again, pushing very hard with one of the commercial leaders in the world of drip irrigation to get these out to market. And you know, I think this is another good lesson for all of you trying to innovate in this space, that even if you have a perfect technology that seemingly really perfectly meets the market standard, commercialization is never easy, and and so we've had to kind of migrate from them, and we're now interacting with potentially a new company, and that takes time, but we are very committed to getting this out to market, and we're quite excited about the impact we think we can make worldwide. So to wrap up, I want to just reflect again on this price performance curve I showed in the intro of the presentation, and how it really captures what we've done in all the 3 projects I talked to you about today. So in the desalination project, this really started by understanding market constraints, really elucidated by our partner Tata Projects, and seeing the opportunity for new technology. And then with the investment of Tata, as well as other funders, UNICEF and USAID, we were able to make these disruptive solutions that are high performance, low cost. And now we're pushing really hard to commercialize these in a number of different spaces. We work with Eureka Forbes, the market leader of small scale home use systems in India. We work with Suez, the world leader in EV systems. And we've actually gotten a lot of funding from the US Bureau of Reclamation to make systems that can work in the southwest of the United States, where people also have brackish groundwater, and it's economically favorable if you could operate systems with solar power. Very similar story to the prosthetic foot project. We started with working with one of the world leaders in prosthetic foot design to understand what users wanted and understand opportunities and what would constitute success. Then we got funding from a variety of sources, a center at MIT and our National Science Foundation. And now we are pushing hard to commercialize this technology globally. And I think one aspect of this project that I really like, as far as the reverse innovation, is one of our main sponsors has been the US Department of Defense, because they also want ruggedized, high performance, low cost limbs for soldiers who want to go back to active duty in harsh environments, who have lost a limb, or veterans that want to be active, as well as working with well-established Western companies like Vibram, and even McLaren, the race car team. We worked with a subsidiary of them to figure out the optimization of this foot. So we really are working in a global space to bring this technology to fruition. And then finally, same story with drip irrigation. We started with Jane, one of the market leaders, understanding what are the barriers to really expanding drip irrigation in the small farmer markets, got funding from Jane and USAID to realize the technology. And now we're working with USAID, one of the leading pump companies in the world, Xylem, and one of the leading chemical companies, BASF, that can help us make lower cost materials for these drip systems in order to disseminate this technology globally. So, you know, something I want to instill in you in this presentation is that you can be innovative. You can impact the lives of people in resource constrained settings, but you can also make a big impact financially and globally if you're strategic about thinking about these reverse innovation opportunities. And I would encourage you to try to map out this price performance curve at the beginning of a project, so you can really be aiming for making that impact in poor countries and rich countries concurrently. So with that, that ends my presentation. And if you're interested in seeing more information about what my research group does, you can go to gear.mit.edu, and that's where we have all our papers posted and more descriptions about these projects. And also, if you want to contact me, my email is awinter@mit.edu. So thanks very much for having me today, and I'm happy to take any questions.
impactful. Thank you, Amos, for making such an interesting and impressive presentation, which really links how the technology that we research in institutions, how it translates into something that is usable and that is going to deliver some impact. I'm particularly impressed with the examples that you gave regarding the rollout of these solutions in developing countries' context. In this case is India, and I'm very sure that similar is the situation in terms of the context in Pakistan as well. Of course, there will be always challenges. Now I open the floor for questions.
Hi, I'm really blown away by especially like the medical sort of innovations that you and your team have come up with, especially the wheelchair, which is just remarkable, just how that works and how you've managed to make it so sort of like people in developing countries can use it well as well. In terms of the prosthetic foot, have you got any documented user experiences, sort of like how their experience has been both in like the first world and the third world, and sort of the affordability for the third world country as well?
Sure. So the long-term field pilot we've done has been in India that I mentioned, that had 15 subjects in it. I went through this pretty fast, but the feedback is that, yeah, people like it, and it actually scores better than the existing Jaipur foot. People are more agile in walking in different terrains, and they can walk faster. And walking fast is an important metric in that, again, it goes back to the aesthetics of looking disabled, and it's also just convenient that you're not walking around really slowly. So this was a very important trial for us because it exposed the feet to really harsh real world conditions, and we had people walking many kilometers per day. They were using the feet in very rigorous activities like pushing vegetable carts or working in the field as farmers. And it was quite exciting to see that there was no physical degradation of the foot. And this was important to test in the real world because you can see there's a material difference between what's called the keel, the main load-bearing structure in the foot, as well as the cosmetic covering, which is made from polyurethane foam. It's made from actually the same material as in the foam of like a tennis shoe. We also saw that the sole was very robust. It's basically a hiking boot sole. So we are planning right now, actually, to your question about in wealthier countries, we just yesterday submitted a very large proposal to the U.S. Department of Defense, where we want to do a quite big trial with the market leader in provision of prosthetic limbs in the United States. It's a company called Hanger, and they have clinics all over the country, and they are by far the biggest volume distributor. And also, as a collaborator on this project, is I would say the leading manufacturer feet in the world. So I want to actually touch on a comment Fayez made in his remarks right at the end, is about the commercialization aspect of this. There's a few things that I'd love to impart on the audience. One, the more you can understand your design requirements for commercialization at the beginning of a project, the better position you're going to be. And I think a big challenge that's faced by a lot of academic work is people will have amazing ideas, really creative ideas, get funding for the ideas, develop the ideas in the lab, see that, it's faster or more energy or less weight or et cetera, really exciting metrics of performance. And only then, after many years of work, say, maybe we can commercialize this. And they may find that because the technology is too expensive or unreliable, or users don't like the look of it, or it smells weird, that it fails. And I often refer to these additional requirements as secondary requirements. They're often not the main driver behind the innovation, but they're critical in its success in an actual market setting. And so for us, that's very much the case in like this foot project, that the core innovation has happened around this keel, this load-bearing structure that incredibly efficiently stores and releases energy, actually even better than the highest performing limbs on the market. But it doesn't look anything like a foot. And for many years, as we test prototypes with stakeholders in India, they'd say things like, yeah, it walks great, but I'd never wear it because it looks terrible. It doesn't look like a foot. And so that's why we had to do this hand-in-hand innovation process of understanding, you know, from a science perspective, how do we make the foot perform as we want, you know, as an engineer, as well as make the aesthetics work, as well as make the price point work. You just mentioned that, Rita, that we had to be very sensitive to what is the price point of the Jaipur foot and can we match it? And so, you know, this foot costs dramatically less money than most other prosthetic feet on the market, particularly those that perform as well mechanically. And we were in this exact situation I talked about in the beginning, where existing feet were here, we had to be here, and we had to figure out how to make that jump. And again, you know, if I can impart on you, if you can try to see all the constraints of this new price performance point and what it would take to be successful there, at the beginning of the project, you are going to very powerfully set yourself up for success down the road.
Thank you, Rita, and thank you, Amos. I think it's quite interesting, just me sharing a little bit of my experience of working in, when I was based at Imperial College London. I come from the water resources and water scarcity side of things. So at that moment, we, as part of our research, trialed a low flow flush toilets. Typically, the toilet flush contributes about 9 liters of water per flush. So what innovation we brought in was consuming around 1.2 liters. And it took us around 15 years to get the product out into the market, and it has been rolled out now. It does take time. And then the other thing which is very important, I think, is that engaging the users, the end users, as early as possible is really going to help. Going back to Amos, on issues like one example you gave on drip irrigation. The common issue, I think, in India and Pakistan, these things have been tried. I mean, not your stuff, but some earlier stuff has been tried with a huge kind of dissatisfaction with respect to clogging of these nozzles. How was your experience in terms of and I think that is mainly because of lack of end user education or lack of operation and maintenance guidance given in local languages. How has been your experience with those irrigation?
You're exactly right that clogging is a major factor in drip irrigation. And that was part of the testing that we did, and we demonstrated in that, I didn't show the plot here, but demonstrated in this study that our drippers are no more or prone to clogging than other drippers on the market. And the way you prevent clogging is with pre-filtration, and then oftentimes like citric acid addition to dissolve any scalants that build up. And so you're certainly right that farmer education is important. Now, that said, we are absolutely working on new variants that are more clog preventing than existing products. And we have a number of architectures that we're actually making some prototypes right now to send to one of the market leaders in this space, because we recognize that important usage factor. And I think you're exactly right that, like, you made the comment, it's so important to connect with end users. And it's important to understand those factors, like I was saying before, that go beyond the core technology, which in our case is low pressure drippers. But we have to think about that technology operating in an ecosystem, which is like user practice. And actually, another good point in that regard is, you notice, we say half the pumping power here, but we only hit 43%. We actually hit closer to 60% in most of the farms. We had one farm, because of user error, they were overdriving the system with higher pressure than necessary, and it threw off our data. As we've gone through the second year of this pilot, this was for the first year, second year, we're getting like 60% energy savings at these farms. So as designers, we can't be myopic about only focusing on the technical aspects. We have to think about the broader ramifications. And I think as far as rolling out a successful system, it's going to require, you know, technology, financial considerations, as well as training of the farmers so they use the technology correctly.
Thank you, Amos. Quite insightful talk, which indeed is going to help. And I think by having today's talk, we are opening up some discussion lines, maybe in the future, for rolling these things out or exploring some commercialization ventures in Pakistan as well. I'm sure we have got some government officials attending this talk as well. So if they are interested, I'm sure there will be some offline conversation as well.
Professor Moss, I have a question. I know, as in academia, you've been it's always interesting to see these amazing efforts or like contribution in innovation and development of these solution, right? So as in academia, what were the key challenges you had to face in dealing with government, right? You've been dealing with various governments, right?
Yeah.
So, and what will be your recommendation for government to design a regulatory framework that supports the sustainable development, right?
Great. Thank you for that question. This is such a great question because there's a lot of sides to it I want to touch on, or a few sides. So one, we had to get local government approval when we did these field tests and we have collaborated both in Jordan and Morocco with the Ministry of Agriculture research arms. They both have research centers, and we've actually done a number of this testing at their test farms. So it was very important to get that buy-in in that interest. The second point is that it's so important to understand the financial structures of the farming markets in different countries. And in that regard, Morocco is incredibly compelling for drip irrigation because one, they're trying to promote it in order to conserve water, but two, they're also promoting solar powered agriculture in general. So that has really primed the market for adoption of this technology because there's big government subsidies to try to promote it. And then the third factor you mentioned about being an academic in this space, that's an important point I want to touch on quickly, is that I think oftentimes I hear from people who want to do high impact applied work that it sometimes is looked down upon in an academic environment because it is applied and people don't think it's fundamental enough and there's not enough like academic rigor or publishability of the work. And that's totally bogus. That's absolutely not true. And the way I always put it is by saying, okay, we are focusing on problems that affect billions of people, often in life or death ways, and they've persisted for decades because nobody has a solution to them. And our existing technologies don't work. So what better foundation for new technology creation and new knowledge advancement could you ask for? You know, and it's very much, I like to make the analogy with Louis Pasteur. Like Louis Pasteur invented pasteurization. Mm-hmm. And he was very concerned about the applied problem, but he was like one of the greatest scientists of all time. But his scientific contributions literally benefit billions of people a day by making milk safe to drink. And so I think as academics, if we can put ourselves in these positions to find problems that require knowledge creation to solve, and if you do so, you can create a real world impact, then you get the best of both worlds. You're doing applied work that can impact people's lives, and you can produce the academic outputs that are expected for, you know, particularly a research group at a place like MIT.
Hello, can all of you hear me? I have been just informed by our technical team who have been monitoring Facebook live streaming. And I am very pleased that we have around 300 attendees for this talk, which is really impressive. Let's see how it goes. We should bear in mind that in Pakistan it's flooding as well. and then lots of continuous power shortages. You might have seen these things in India as well, but despite all things, which is quite encouraging. Shall we thank Amos in our usual way for spending time with us? We do realize that it takes considerable time to develop the presentation, organize your thoughts, and make it very much audience relevant. How to Amos? I mean, I can clap for myself. I hope you fun as well. Now, thank you very much. The next talk that we have is on 16th of September. That's going to be on Sunday, and it's going to be a talk from a professor from Imperial College called Professor Mike Templeton, and he's going to talk about sustainable sanitation for all, which in a way Amos did touch upon while explaining these sustainable development goals. Thank you all participants. Now we have to close that meeting, and we do appreciate your interest and engagement, and we will continue to relay and try to bridge the gap between the communities, between the generations, and between the academia and then the commercial sector as well. Thank you very much. Bye.